Hello, and welcome to the problem-solving skills segment of this video. In this segment, we'll be looking at various problem-solving skills that you'll need as an architect. So when you think about solving problems, most of the problems we think about solving were those, for instance, from grade school math. For example, using the Pythagorean theorem to find x, or expanding a simple polynomial. Now, when we think about these problems, when we look back, especially as an architect, we realize how simple those problems are. However, as an architect, a lot of times we're faced with really complex and difficult problems. These may relate to architecture, team process, team dynamics, requirements, and so on. So fortunately for us, most problem-solving skills have a basis in mathematics. And because of that, we're able to leverage these skills and apply those to the IT industry, not only as a developer, but also as an architect. So in 1945, Professor Polya from Stanford University wrote this book, How to Solve It. And in this book, which was written in 1945, he introduced something called this checklist. So what Professor Polya says, whenever approaching a problem, specifically mathematically, but in general when approaching a problem, the first step is really to understand the problem. The second step then, once you have an understanding of the problem, is to devise a plan. The third step in any sort of problem-solving exercise is to carry out that plan. And then, Professor Polya says, the fourth step is to do a retrospective and look back to see if we can validate the problem. So let's take a detailed look at each of these steps in this checklist so that we can kind of gain an understanding of at least one basic foundational process for solving problems that we'll encounter as architects. So step one is understanding the problem. What we're really trying to do here is before beginning, try to gain an understanding of the problem. Ask yourself these following questions. For example, what is the unknown? What is it that we're really trying to solve with this particular problem? What are the data, conditions, and constraints? Also ask yourself, can you draw a figure or diagram to represent the problem? Now this one step here is going to be probably the most important step or aspect in this entire checklist, and consequently, almost in this entire segment of the video. Can you break apart the problem into separate parts? Would this make the problem easier to understand? So what we're really trying to do here is gain an understanding of the problem, collect all of the data. Once we have that, we can move on to step two, which is devising a plan. Here, what we're really trying to do is find a connection between the data and the unknown. So you ask yourself these following questions. Have you seen this problem or a related one before? Maybe that will help us try to solve this problem. Can you change the problem to match something you did solve before? Because maybe by changing part of the problem, we can actually, in our brains, think about the solution and apply that solution to another problem that we did solve. Can we restate the problem? Now think about this. We did this all the time in grade school mathematics with those word problems. Remember? Mary drives 5 miles south and 6 miles north. Who cares where Mary's driving? What's the equation? And we would restate those kind of problems in terms of equations. Okay. So can we restate the problem? Can you solve part of the problem? This is another aspect. Maybe we can't solve the whole thing, but can we solve part of it? Or can you solve it by removing or changing part of the condition? Can we derive anything else from the available data? So what we're really trying to do here is find that connection and really devise a plan. The third step is really executing that plan, checking and revising each step along the way. So we ask ourselves these questions as we're executing or have executed the plan. Can you prove that the result is correct? So also ask, did you use all the available data? And this is a critical step in this process. Many times we'll come up with a perfect architectural solution, but forget certain conditions, constraints, or other data aspects. Did you use the whole condition? Did you apply all of the constraints? This is a key part when you're carrying out your plan, arriving at like, for example, an architecture and saying, okay, I think this will work. Did we use all the constraints, the conditions, and all the data available to us? And finally, in step four, we look back and do a retrospective and examine the results. Can we check the results? Can we, quote, like, do the math? Does it make sense? Can we see the problem at a glance? In other words, once we solve the problem after weeks and weeks of work, it's like, oh, that was so easy. I should have seen that before. These are good indicators that the problem has been solved correctly. But can we derive the results differently is also another way of really proving that we found the right results. So what I would like to do now is run through a little problem exercising some of this checklist to see where you can actually leverage this to answer a problem. So this is titled, What Color Was the Bear? So a bear starting at point P walked 1 mile due south, then he changed direction and walked 1 mile due east. Then he turned again to the left and walked 1 mile due north, arriving exactly at the point P from which he started from. So the question is, what color was the bear? Well, if we look at the checklist, what is the unknown? What are we trying to solve? The color of the bear. What is the data? It looks like we're given some sort of geometric progression on the globe. So when we go to step 2, devising a plan, what is the connection between the data and the unknown? Seemingly, there's really no connection here, but we plug ahead and realize that's probably a geometric progression. And can you guess where that is? That's right. Chances are it is the North Pole, right? Because if we have the North Pole as our point P, if we walk 1 mile due south, then east, then north, we'll arrive at the same point. That can only happen on the North Pole. So now that we've actually applied the data, we can answer the question, what color is the bear? And of course, you'll probably think in your mind, well, duh, white, right? So let's utilize the checklist to verify that result. So for example, can you prove that your result is correct? Are you really sure about your answer? Are you willing to bet money that that bear is white? Could there possibly be another answer? So if you say no, you might in fact be losing the bet, because is there another place on the globe where this geometric progression exists? And in fact, there is. It exists on the South Pole. If you travel up the 1 mile meridian mark and you go south exactly 1 mile, east exactly 1 mile, right around in a circle, and go straight back north, you will arrive at exactly the point P. So in fact, there are 2 geometric progressions described here. So what color is the bear? Suddenly we're not so sure of ourselves. Is this another alternative? We did try to derive the results differently. Is the answer still white? Well, we apply knowledge and say, well, let me Google what color are the bears in the South Pole. And what you will realize if you Google this, that there are no bears in the South Pole. So therefore, yes, the color is white. So you can kind of see exercising this checklist in terms of all the different steps. Immediately you might say white without even checking your results. However, there was another viable alternative. Turns out since there's no bears, it wasn't. Okay, so we have validated and verified our answer. Okay, so another technique in problem solving, and we're going to be using this checklist kind of as a basis throughout, is visual representations. Now, whenever we go to solve a problem, one of the most powerful and important steps in solving complex problems is drawing a visual representation. Let's face it, as architects, what's the first thing we do when we go into a meeting to try to form a solution? We grab a dry erase marker and go to the whiteboard. We start visualizing the problem. And this is a very, very powerful technique. So whether we visualize it in terms of a wireframe, lines and boxes to be able to actually see the problem, whether we create lists of numbers and sets, regardless of how we do this, this does something special, something different to the brain. It allows us to kind of see the problem and see a different perspective of the problem from our brain's perspective. So let's see how this might work to solve a particular problem. Now, there's going to be multiple facets in this particular quiz. So how old are my 3 sons? So here's the scenario. 2 friends meet after not seeing each other for a very long time. One friend tries to guess how old the other friend's 3 sons are. Since they're geeks like we are, they're doing this little mathematical game. So friend 1 says, hey, guess what? All 3 sons celebrate their birthday today. Can you guess the ages? And friend 2 says, oh, sure, I can guess their ages, but I'll need some information first. And friend 2, of course, is like a mathematician. So friend 1 says, ha, ha, ha. Okay, the product of their ages is 36. friend 2 thinks about it and says, I'll need some more information. Okay, the sum of their ages is equal to the number of windows in that building right over there. That's kind of weird, but friend 2 says, okay, I almost have it. However, I just need one little more piece of information. And so friend 1 says, okay, my oldest son has blue eyes. And friend 2 says, ha, I know the ages of your sons. Oh boy, so looking at this, what is the unknown? If we kind of apply the checklist, the ages of the 3 sons. What do we have available as data? Well, looks like kind of a mathematical expression, doesn't it? In terms of the product of their ages is 36, and the sum is equal to the number of windows in that building right over there. So what I'd like you to do at this point, if you want to, is to pause the video and try to see if you can work out the solution. Focus on the approach and what you would do. So I'm guessing your first thought, or the first thing you wrote down on the piece of paper, was to say A times B times C equals 36. Certainly that's the product of their ages. You probably also wrote down A plus B plus C equals W for the number of windows. What are we going to do if my oldest son has blue eyes? Well, we can't really do that mathematically, and we also recognize that we have 2 equations with 4 variables, so we can't solve this particular equation. So this was an attempt to say, well, let me try to solve it mathematically. So does this seem a little bit difficult now? Yes. In fact, now it's like I have no idea what to do. Well, let's take a look at the facts and think about the section of this segment we're in. Visualizations, visual representations, and I'll show you how powerful these are in actually seeing the problem actually unfold. So the product of their ages is 36. Well, if we draw a table to represent the factors of that, we already see and form what's called a solution set. And we can see that 1 out of these 8 combinations of numbers is in fact the answer. So we are looking at the answer, but we still can't form it yet. But as you can see, the problem doesn't seem so complex now. Let's move forward on another one. The sum of the ages is equal to the number of windows in that building over there. Well, if we draw this table, here's the factors. If we add them up, we see that the number of windows is 38, 21, 16, 14, 13, 13, 11, 10. Visual representations of a problem are so powerful because if you look here, you can kind of see more information, right? For example, there's other aspects of this problem that we can also derive. So do you remember in the checklist, the last part of step 2, can we derive anything from the available data? The conversation itself is data. The conversations you have with users in terms of gathering requirements, with various stakeholders as an architect in terms of interpreting requirements, understanding those, that conversation flow is also data. You can consider it metadata. But consider this. What was that last question? Or what was the last kind of dialogue? I almost had it, but I'll need one more piece of information. Can you guess at this point what the 2 possibilities are? That's right. It has to be one of these 2. Why? Because the conversations that you have with individuals, with people, is data. He had to ask a third question because if there were 21 windows in that building, how old would the sons be? 18, 2, and 1. But in fact, he saw 13 windows. He had to because why? He had to ask for another piece of information. And what was that presumably irrelevant piece of information? Well, it was that my oldest son has blue eyes. Now, these are terms that we may hear from gathering requirements or talking with various stakeholders as an architect that we throw away. Well, I really don't care about your son and his blue eyes. However, this helps us answer the question because what's the relevant information here? It's not that he has blue eyes. It's the fact that there's an oldest son. So that means 6, 6, 1 is not possible. So the answer, of course, is 9, 2, and 2. Okay? So we've seen many different facets here. We've seen the fact that being able to draw a visual representation of the problem helps solve almost every complex problem we have. It helps get your mind around it. We also see that seemingly irrelevant data is in fact critical, important data, and in this case, the only data that we were able to use to solve the problem. Thirdly, we also saw that the flow of conversation is data itself, and sometimes the ordering of that flow. Okay, let's look at another technique in problem solving, and this is knowing what happens when you assume. And of course, we all know what that adage is. This is what we're talking about here, is really limiting assumptions. Whether you know it or not, we as IT professionals make limiting assumptions all the time. For example, time is a limiting assumption. The phrase is, we don't have the time to implement that feature. That's not true. It's a limiting assumption that we are placing on ourselves, restricting us from the ability to solve that problem. For example, can the solution be done quicker? Can it be iterated? If we want to be able to put a certain piece of functionality in, and we don't have time for that, well, can we iterate it then? Can we get part of it in now and part of it later? So that's an example of a limiting assumption. Money is another big limiting assumption. Oh, you can't do that. We don't have enough budget to implement that feature. So we just don't do it. Well, the counter to that particular limiting assumption is, well, can I find more money? Can I produce a cheaper solution? Can maybe I move to open source instead? Can I borrow money from some other project that's doing really well? So these are some responses to that particular limiting assumption. There's a couple more limiting assumptions that are said all the time. Are you kidding? That'd be impossible to implement. Well, that's a limiting assumption based on physics. Wait a minute. Is it really physically impossible? It may be overly difficult, but is it really impossible? Implementing a 5 nines availability architecture, which is downtime of a little more than 5 minutes a year, coupled with sub-second response time, is not impossible. It's extremely costly and extremely difficult. However, processing data between Boston and San Francisco in 0.00003 nanoseconds is in fact impossible. Electrons don't travel that fast. So whenever you say something's impossible, make sure you qualify that by saying it's really not impossible, but it's too costly or too difficult to implement. There's one final limiting assumption here, and that is of laws and regulations. Oh, no, we can't do that. There's laws from preventing us from doing that. Well, guess what? There's lobbyist groups to be able to change laws or to reinterpret laws. Can we break the law? For example, we would like to implement a certain feature, but it's going to cause us a delay in generating the fund prices at the end of the day. So we say, well, by law, we have to have those fund prices out at 4:40. And it's like, well, what if we're at 4:45? Well, then we'll get written up. It's like, oh, how scary. Go ahead and implement that feature. Versus, well, we're fined about $2 million for every minute those fund prices aren't there. It's like, well, okay, that's a good reason not to implement this feature. So, okay, so there's some techniques when we talk about assumptions. The first is most projects or problems that you have, you will have to form assumptions. So my technique is to make a list of those assumptions behind the problem or the specific type of architecture, for example, that we're trying to solve. Okay. I usually put these into a spreadsheet, for example. And then the second step, ask, are these assumptions correct? Can we verify them? So what I have in this spreadsheet are various columns. So I'll have a column for, can it be verified? Is it verifiable? And can it be verified? Is it verified? So on and so forth. So that we can have an assumption and say, well, I'm guessing this is going to need to be up 24/7. It's like, well, that's kind of an assumption. Can we validate that assumption? And the answer is, well, of course. We can go to the stakeholders and ask them, do we really need continuous availability for this particular architecture? Whereas other assumptions that we make are ones that may not be able to be verified. And the other tip is to watch out for the obvious assumptions, because these are the ones that are usually wrong. Case in point, this is a picture of a woman's swimsuit. Now, for decades and decades and decades, women's swimwear was quite simply ugly. It was really a funk in the women's swimsuit industry. Why were they so baggy and kind of burlap-like? Well, and this is a true story, swimsuit manufacturers were not able to find a material that was durable enough to withstand the high chlorination of swimming pools and the high salt content of oceans. Quite simply, that kind of fabric just didn't exist. So instead, really thick fabrics that tried to accomplish both of those were produced, resulting in some pretty ugly pieces of swimwear. Well, one gentleman in the swimwear industry really got tired of looking at all these really horrible looking swimsuits, and he decided to challenge an assumption in the industry. Do you know what that assumption was? You can probably guess. The assumption he challenged was that women actually swim in swimwear. Now, when he stated this, he was essentially called a fool and ousted from the whole swimwear industry, but he did not give up. He continued to spend years in gathering metrics and analysis and data, and in fact, it turned out that he was correct. Most women use swimwear to lounge or to hang on the beach or to hang by the poolside. Very rarely do women put on a swimsuit to exclusively swim. So with this information on the table, it basically revolutionized the swimwear industry for women. Now, if we could do something for men, that would be really, really good. So here's a problem to try to solve. I didn't know that firemen drank that way. So a man ordered a glass of red wine and white wine at a bar. He took the glass of white wine in his right hand, the one with red in his left hand, and he drank them both. The next day, as he did the same. When he was leaving, the bartender asked, "I didn't know firemen drank that way." The question is, how did the bartender know he was a fireman? So let's go through Polya's checklist. What is the data? The data here is that we have a glass of red wine and white wine. In both hands, then he kind of drank them both. He was leaving, the bartender asked, "I didn't know firemen drank that way." So somehow the bartender seems to know he was a fireman. What's the unknown? That he knew he was a fireman. Is there any connection that you can see here between the data and the unknown? Well, red and white, kind of fire and water, there may be some connection there, so we can chalk that up on a little whiteboard. He drank both red and white. Anything else? I really don't see a whole lot. So you can kind of see the problem. We have to solve this problem. Can we derive any data? Well, don't see anything that we can really derive other than the left and right hand. So clearly here we have a problem we need to solve and we don't have all the available data. What would you say is a good rational reason that the bartender knew he was a fireman? How about because he pulled up in a fire truck? Well, how do you know that? It's not in the problem statement. That's right, I have to make an assumption. Oh, that's a stupid assumption. Well, I think it's a valid one. Let's write it down. So we'll write down, pulled up in a fire truck. How about another one? Oh, I got it. He was wearing a fireman's outfit. Let's write that one down. So you can see what we're doing. We're forming a list of assumptions. Let's do one more. There had been a fire the previous week, and this was the gentleman who was working at the time who put out the fire, so he got to know the fireman, or he got to know the bartender. Okay, so we put that one up. Okay, let's limit it to those assumptions. The next step of this process is to try to validate those assumptions collectively as a group. He pulled up in a fire truck. Well, it's certainly possible, but I'm guessing that's probably not reasonable use of a fire truck, right? I mean, if you're driving a fire truck and pulling up to a bar, I'm guessing that that's probably some law against that. So that's kind of a silly assumption. So let's mark that as silly. Okay. He was wearing a fireman's outfit. Well, my guess is that he's required by law to take that fireman's outfit off. So that also seems maybe a little silly. There was a fire the previous week. Well, we have no idea, but that seems reasonable. Okay. So we'll say there was a fire that previous week and he got to know the bartender for that. But you can kind of see the point here through this exercise. Without making assumptions, we cannot solve the problem. So in almost every problem we have as architects, you will have to form assumptions in order to solve the particular problem. The trick is, which assumptions can we validate and which ones do we have to kind of vote on to say it's most reasonable? Okay, let's look at another technique in problem solving, and I like to call this, hey, keep it clean. Interesting little title, but this is all about redirecting. So oftentimes, the best way to solve a problem is simply to walk away. We all have various techniques to be able to kind of refocus our brain. Mine in particular happens to be taking a shower. Whenever I'm faced with a problem I can't solve, whenever I just go and take a shower, the problems just seem to come out. As a matter of fact, this was so common that I ended up getting the water-soluble markers and writing down all these little things because I was afraid I was going to forget them on the shower stall, which was a little bit silly. But other techniques, such as taking a walk around the building, going out for a beer, grabbing a smoke, just going and talking to somebody, grabbing a cup of coffee, whatever your particular solution, what I would encourage you is to really think about this right now and think, gee, that's right, what do I do? Every time I'm just flustered with something, I just walk away. Think of this scenario here. Let's say I'm coding away and I'm trying to throw a particular exception. And I see the code and the exception's not being thrown. Darn, it worked. Darn, it worked. And you get all flustered. So you grab your laptop, you storm on over to John, you throw your laptop down and say, John, look at this problem. All I'm trying to do is solve, oh, I see why the exception's not being thrown. Thanks, John. And you storm back over to your desk. John, meanwhile, goes, what a weirdo. But the point is, you redirected. You walked away from that problem. You're explaining the problem to somebody else. How many times, like especially in a developer mode, or even when you're trying to create a very complex architecture, have you been really stumped and you try to explain the problem to somebody and it immediately comes to you? Well, there's a scientific reason why it's good to go and grab a beer at the pub when you're faced with an incredibly hard problem. And that is because doing something else, any of those little techniques that I just mentioned or the ones that you have, basically tends to refocus and redirect, and it reduces the activity in the prefrontal cortex of your brain. And that's where all the logical thought is. And it's a very small part of your brain. So by walking away, effectively, you are allowing creativity to flow. So really the best way to think about this is logic really is creativity's kryptonite. And the more you focus and think on the problem, the less likely it is that you're going to actually solve the problem. Think about how many times you went to bed in the morning, it was just painfully obvious. It's because we didn't apply logic, we applied creativity. Okay. Another very powerful technique is knowing that the world is in fact flat. Okay. What does this have to do with anything? Well, it's about using the right representation and model to form your problem. You see, when solving real-world problems, you have to first create a model. Now, the idea here is this is implicit. You are always creating a model when you solve a problem, whether you know it or not. Now, it's interesting that the size of the solution space, in other words, the realm of possible solutions, is really not determined by the problem. In fact, it's determined by the representation we place on that problem. And the thing to remember by this is every single model leaves something out. So the best way to think about this is, of course, map projections. So when projecting a map of the Earth, for example, only one of the 4 basic characteristics is preserved. In other words, distance, direction, shape, or area. For example, the Mercator map projection is the only single map projection that exists that preserves shape. The vertical perspective preserves direction. All other aspects are distorted. The Moweed is the only one that represents area, and the equirectangular is the only one that preserves distance. So all other characteristics are distorted. So let's apply this to kind of our industry. Let's say that you are asked to design a user interface to place orders. Well, the solution space is very large, right? Because we have not applied a model to it. Does this need to be kind of a fat client Windows app? Does it need to be a CICS screen, or are we really talking about a web app here? Oh, well, of course, I thought that was obvious. We're talking about a web application here. So you can kind of see that the solution space, in other words, if we turn this into IT, the solution space of technology and techniques available is now limited. But it's not limited by the problem, design a user interface. It's limited by the solution space that we imposed on it to make it a web-based interface as opposed to a CICS green screen. Furthermore, what type of user interface to place orders is that? Because we have to further qualify our representation or model to say, well, is this to place trading orders, or is this simply an order like on eBay, for example, or some sort of e-commerce website? Because the solution space to design such a solution is dependent on one of those two answers. So here's what I'd like you to do to be able to really visualize this whole concept. What I'd like you to do is hit pause and go find 6 matches. Now these can come from a matchbook or they could be wooden matches. It really doesn't matter. If you can't find them, then just cut out 6 equal length pieces of paper. Now what I'd like you to do is to construct 4 equilateral triangles. These are triangles with all the sides the same length, where the length of each side is equal to the length of each match. In other words, you're not allowed to break the matches. You have to leave them the same length they are. Okay? So what I'd like you to do is hit pause and try to puzzle out this problem. See if you can find the solution. So hopefully you came up with the answer. If you didn't, let me show you the little trick to this. I'm sure most of you were able to form this kind of diagram. That is rather easy, but it's not 4 triangles. As a matter of fact, this solution, in fact, is completely impossible. Why? Because what sort of representation and model have we placed on this problem? The matches are on the table. The table is a 2-dimensional space. That is the representation we placed on it, even though we didn't know it. So if we change our model to a 3-dimensional space, this is a painfully easy problem to solve. So if you want to get a few extra drinks at the bar, kind of sitting there with some matches, just turn to your buddy next to you and say, hey, I'll bet you a beer that you can't do this. And of course, hopefully they can't, and just show them that you can, and you'll be able to drink beer all night long. Okay, fantastic. So here's another interesting problem-solving technique. We should take the trail to the left, I think. Now, I'm an avid hiker, and so I really like this kind of problem-solving piece of getting lost, basically. But this technique is all about maintaining focus. So what are you trying to solve? What are you trying to convey? And the problem is, in our industry, whether you're a developer or a designer or an architect or anything else, the problem that we love to do is to make things more complex. We do this because we lose sight of the goal. We take tangents and tangents upon other tangents, and we also love to create additional complexity. Both of these things take us further and further and further away from our goal. So the key here is to say, what are we trying to solve? What are we trying to convey? A very good example of this is this particular architecture diagram. This looks really horrible, and as a matter of fact, it is really horrible. This is supposed to convey the major information flows of the back-end processing of a major bank. Can you figure this out? I can't. So we've made this unnecessarily complex, something I alluded to in a previous video segment on accidental complexity. So how do we get into this position? Well, it could just be simply that we're trying to do job security, for example, but in most cases, we start out with the simplest of problems. So I need you to diagram the major information flows of all the back-end processing. And so you do that. You start validating that with various stakeholders, and somebody might say, well, you've got the account reconciliation as just one box. As a matter of fact, there's 4 or 5 components there on that. I think you should split that out because each of those have different information. And you're like, I guess that's true. So you do that. You go to other stakeholders. Well, you should also indicate the operating system and the protocols used for that. I think that's very important because along with data, you also need the transport along with that. And it's like, yeah, that's pretty relevant information too. And this goes on and on and on and on until you have a diagram that includes about 5 or 6 different views lumped together, which looks like this. So the real trick in terms of maintaining focus is really, and not getting lost, is really to create views and don't lose sight of your purpose. So what I typically do whenever I'm faced with this kind of exercise is, whether I'm using OmniGraph or Visio or whichever tool, at the very top, as you can see here, I put in bold red, I keep an area for a purpose statement. Now, I don't always put it on there, but if I start to recognize that I'm talking with somebody and say, you should really split that up, or, oh, you should really put the protocols or add the databases there, what I'll do is I'll stop and I'll say, what's the real purpose of this view? What am I trying to convey? What am I trying to solve here? I'm trying to convey the major information flows. That has nothing to do with the access protocols or splitting up applications into multiple parts to visualize those. So therefore, I'm going to write that at the top of that view. Information flows, and I'm going to focus big, bold red on there. The other information is very critical, and in fact, I'm going to record those things on other views. And so this is a pretty easy solution to this particular problem in terms of techniques of solving problems of documenting architectures. I'd like to close with one final problem-solving technique, and that is that perception can be reality. So here's the question for you that's somewhat meta and philosophical. Often the best way to solve a problem is not to solve the root cause of that problem, but rather to create the perception that you solved that problem. And the question is this really solving the problem? Let's say we're having some very serious performance issues in our web application. So you start looking at it and it's like, whoa, this is really bad. But you also notice one thing, that between screens, you've got some think time by the user. And so you leverage that think time to be able to cache data so that the screens are much more responsive. You implement that change, and the users are ecstatic. Hey, you fixed it. This is almost sub-second. This is exactly where we want it to be. Now, the root cause of the problem is certainly bad SQL, untuned database, so on and so forth. The question is, have you really solved the problem? There's something in our industry, or in the elevator industry, I should say, called door dwell. You know how impatient you get when you go into an elevator and all of a sudden the doors aren't closing? What's the first thing you do, especially if you're in a hurry? You hit the door close button, don't you? Guess what? 99% of all elevators don't have an enabled door close button. Why? Well, because early on, most building managers were very afraid of lawsuits, of actually somebody pressing that door close button when somebody was walking through and trapping a limb or something in between the doors. So they started disabling them, and now by default, the door close button is in fact disabled. Now, some companies can, of course, by request, enable it. But the point is this. You're standing there, the doors aren't closing. The doors take about 3.5 to 4 seconds to close. So what happens? You wait a couple seconds, what do? You start pressing on that door close button for about 2 seconds. And finally the doors close, and you say, oh, finally. You're not doing a thing. But did it solve door dwell? It's a good question, because the elevator time of those doors closing did not stop. But the perception by the person in the elevator is that they have. The reverse is also true of a door dwell when you're waiting for an elevator. How many times have you stood there, you press the down button, and you're waiting, and you start to get more and more impatient? You start huffing and puffing. It's like, come on, I got to get going. The door's finally open, you rush in, and of course the first thing is you start hitting that door close button, right? Well, that waiting has really been solved by what? How many times have you noticed, and as a matter of fact, the next time you go to an elevator in a building, or especially a hotel, turn around, because guess what's there? A mirror. So you press the button, you turn around, and there's a mirror there. It's like, oh, looking pretty good today. Ding! Whoop! And then you rush off. In other words, it takes the same amount of time for that elevator to come up to your floor, but the perception is, because you were distracted by the mirror, it was much faster. So, by not fixing the root cause of the problem, are you really solving the problem? It's something cool to think about, because as an architect, you're going to be faced with many, many problems to solve. Sometimes getting to the root cause of that problem is going to be tremendously hard. So one solution is to try to solve the problem through perception. So for more information, you can certainly try to find the How to Solve It book by Professor Puglia. It was written in 1945, so it's very prescriptive. The teacher and the student shall not have a close relationship because the student must be able to solve these problems on their own, right? A much more modern version of that is How to Solve It Modern Heuristics by David Fogel and his counterpart, which I'm not going to try to pronounce that name. So these will provide much more in-depth knowledge into the art of problem solving, especially with such things as the travel salesman problem and so on. So this has been the problem solving skills segment of this video, and thanks for watching.